Okay, hi everyone. Thanks for tuning in today. So it's my great pleasure to welcome Antonio here today. He's an assistant professor at the University of Pisa, but he's also a member of Continual AI, which is a non-profit organization, and I think this is a very interesting stuff, interesting idea. And also maintainer or lead the maintainer of Avalanche, and which is going to present today. So with that, floor is yours.
Okay, thank you for the introduction. So today I'm going to present you Avalanche, which is a library for continual learning research. Okay, wait. This is a library developed by Continual AI, which is an open group of researchers on continual learning. And here today I'm presenting the library to you, but there are a lot of other people working on the library, like Andrea, Lorenzo, Gabriele, Ahmed, and Vincenzo are the core maintainers of the project, but we have also many more contributors which have helped the library become what it is today. So just a quick word about me. You already know I'm Antonio Carta. I'm an assistant professor at the University of Pisa. I'm working in the Pervasive AI group, and I'm here as a lead maintainer of Avalanche. My research focus is mainly on continual learning, so I have to admit that I don't know a lot about AutoML, but I hope to give you some inspiration, because I think the two fields may be more connected. Right now they are mostly separated communities, but I think there are lots of opportunities to work at the intersection between them. So since I guess not all of you will be familiar with continual learning, first I want to give you a brief introduction just to give you an idea of what continual learning is, why it is important, and also why it is important to have a library to do continual learning. So what are the challenges when you implement continual learning algorithms? In general, the problem of continual learning is the problem of learning from an infinite stream over time. So you have a model, a machine learning model. In our case, I'm assuming most of the time it will be a deep neural network, but of course it can be anything. And you have a stream of data. So imagine these boxes are what we call experiences. And at each time step, you get one experience, which contains either a batch of data, or maybe if you're doing reinforcement learning, it may be an environment or a single example. So depends on the scenario, but the idea is that you get the information inside this batch and you use it to update your model. So like here at time I, you want your model to be able to learn the data of time I, but also to remember all the previous experiences, so from 1 to I. And the main problem in continual learning is that you have some constraints on the learning algorithm. So theoretically, you could imagine that you could just take all the data from the entire stream, combine it together in a single data set, and then train the model in a single step. However, this is very expensive. So if you assume that you have limited computation and limited memory capabilities, typically you're not going to be able to do this joint training on the entire stream, but you have to update the model incrementally. And also sometimes you have other issues like privacy. So you don't want to look at all the data because you don't want to store it at all. So these learning constraints make the problem of learning incrementally much more difficult, of course. Now, just to give you some examples, here are some of the popular benchmarks that you have in the continual learning literature. So let's start with MNIST digits, so an image classification dataset. The most popular thing that people do is to create a stream by creating new classes. So this stream, the data is split by classes, and at each time step, you encounter novel classes. You have the example here in the slide. So the first task is about labels 0 and 1, then you have 2 and 3, and so on. And this is like a very natural kind of shift. So there are many applications where you don't have all the classes at the same time, but new things appear. And so you want to be able to update the model. The other example is the new instance scenario. So where you have that the classes are staying the same, but you have new inputs. This is also called a domain shift. The example, the simple example, this is kind of a toy data set, but just to give you an idea, is permuted MNIST, where you add new inputs by just creating random permutations of the pixel. Of course, and this is completely fake, but there are real scenarios that have this kind of input shift. And then another difference is whether you have task labels or not. So sometimes you have this additional supervision signal, which allows you to split the data into separate tasks. So like here, if I know that an input is about the task 1, I'm going to classify it either with a 0 or a 1. But if I don't know the origin task, then I can say that it's an 8 or 9 maybe. So if you don't have the task label, the problem is much more difficult. And typically, they are not available because it's not something that is feasible in most applications. Now, the problem with continual learning is that you have a thing called catastrophic forgetting. So as soon as the model is trained on new data, the model will quickly forget about the old data. And this is a general result, but in particular, if you have a deep network and you train it by stochastic gradient descent, the forgetting will be very, very quick. So like this is an example from the EWC paper, one of the similar paper for continual learning in deep network, where you have the error. I mean, you have this kind of catastrophic forgetting effect. And if I remember correctly, this is actually average over the tasks, because if you look at it only for the past task, what you see typically is that the model is learning very quickly. And then here there is a task shift, and it's also forgetting very quickly and forgetting more and more over time. So this is really the main problem that you encounter when you're doing continual learning. And like, I'm not going to show you continual learning strategies because I mean, this would be a talk by itself, but I want to make you aware of the kind of challenges that you have when you implement a continual learning strategy for a deep neural network. So the first kind, these are the three main families of continual learning strategies. So the first one is replay. The idea is that in replay, you keep a buffer of the old samples. So this is a very small buffer, not the entire stream. And then you do rehearsal. So you combine data coming from the current experience with a mini batch coming from the buffer. And like you can imagine, like whenever you get a new example from the stream, you can choose whether to add it to the replay buffer or not. And then you have also to remove examples from the replay buffer once you have reached the maximum capacity. The second family is the one of regularization strategies. So in a regularization strategy, you have that you add a regularization term so that the model is able to learn to balance learning on the new task and forgetting the old ones. So you have these two kind of objectives, which are one of the opposite of each other, let's say. So you have to balance these two things. And finally, we have architectural strategies where the model is expanded over time. Like you can imagine that you have a layer with 100 units, and then you over time you want to add new units because at some point the capacity of the model will be full. So you add new column of new units to each layer to increase the capacity of the model. Now, the key idea that you need to understand from this is that in a continual learning strategy, everything is changing over time. So the data that you are using is changing. The regularization function is changing. So the loss criterion that you use to train is changing, and the coefficient that you use are also changing over time. And also the model is updated over time. So you may have to increase the number of parameters and do some other kind of modifications. Now, if you are familiar with PyTorch, you can understand that some of these changes are not that easy to implement. For example, there is no support in PyTorch for implementing like a model that is changing over time, but also even just things like data loaders. Data loaders assume that the data is fixed, and if your data is always changing, the PyTorch data loaders are probably going to be very inefficient. So this is one reason why having a library like Avalanche is useful. So now we start the second part where I'm going to show you the design of Avalanche, its main features, and how you can use all the features that we have in Avalanche. So Avalanche was designed to be a very comprehensive API and consistent. So comprehensive because we have benchmarks, we have models, we have logging and metric computations. So everything that you need to do continual learning is there. It's consistent because like one problem that there is in the continual learning literature is that there are several different nomenclatures. So if you look for some code, for example, on GitHub, implementing a specific paper, then it's very difficult to even understand on what kind of scenario they are testing the model. Instead, in Avalanche, there is a fixed nomenclature, so you know exactly what is happening. Then there is a very easy to use high-level API. So if you just want to run the baseline on a couple of predefined benchmarks, this is something that you can do in like 20 lines of code. It's designed for reproducibility and portability. Actually, we have a repository where we are adding reproducible baseline. So we take the Avalanche implementation and the results of the experiments, and we create a script that is matching the paper. So you can start from that, and you can be sure that Avalanche implementation is actually in line with the literature. And if you need it, Avalanche is also very easy to extend. So it's a modular API, and the low-level API are quite flexible. You can do really customized things with it. And finally, it's a community-driven project. We have, as I said, we have a small team of core contributors and maintainers, but there have been more than 40 contributors, and these are people that committed to the repository, and then many more that are using Avalanche or like helping by posting issues and discussions. So the community is growing. Is growing well. You can install it with pip if you want to test it, so it's very easy to do it. Now, let's see a minimal example. So this is all that you need to do a minimal example using a benchmark already defined from Avalanche and a continual learning strategy that is inside Avalanche. So this 3 lines here are for the definition of the benchmark. The benchmark object is the object that contains the streams of data and the data definitions, basically. So you have the train stream for the training data and the test stream for the test data. Then Avalanche is mostly compatible with PyTorch. So here, the model, the optimizer, and the criterion are PyTorch object. There is nothing weird going on. So if you know PyTorch, there are no surprises here. Then we define the continual learning strategy. So naive is the fine-tuning strategy where you take the new data and you do the gradient descent on the new data without any kind of mitigation for catastrophic forgetting. So you give it the parameters like model, optimizer, criterion, some parameters for the batch size, training epochs, and so on, and you are done. Then to train the model, you can just loop over the experiences in the training stream and call the train method repeatedly. And then the eval method, of course, to get the evaluation results on the test stream. And like inside here, Avalanche is also doing things like logging. So at the end of this loop, you go on TensorBoard and you're going to find all the results. This is the high-level overview of the architecture of the library. So we have the benchmark modules, which is in charge of the data. And from the benchmark, you get the stream of experiences. Then the stream of experiences is passed to the continual learning strategy. The continual learning strategy is coming from the training module, and it's also in charge of updating the model. The model is coming from the models module, but here, I mean, most of the time you can use a PyTorch model, and we have just added a couple of things that are specific to continual learning, but you don't have to use them if you don't need them. Then we have the evaluation module, which is basically the evaluation is taking a set of performance metrics here, P1, PM, and it's communicating with the training loop to update these metrics constantly. And finally, the logging loop, the logging module is taking the metrics and it's serializing them in some specific way. You can have things like printing to the terminal, printing to a file, TensorBoard, I mean, the obvious things. And I mean, we have already made components for all of these, but you can also make your own. So if you want your own logger, it's relatively easy to do it. So as I said before, most of the classic benchmarks, the things that you take from the literature are already available, so you don't have to re-implement them. And if you find that there is something missing, just open an issue and we will probably add it soon. And benchmarks are quite flexible, so you can, like here, split MNIST is the MNIST digits where you do the class-based split. You can ask for the length of the training stream. So here, 5 experiences means 2 classes at a time. You can set the seed for reproducibility, decide whether you want task labels or not, fix the class order, and then change the training and evaluation transformation. So in Avalanche, datasets are based on the Avalanche dataset object. This is just a wrapper over PyTorch datasets that adds a couple of features that we need, like the ability to switch between training and eval transformation, and management of class labels and task labels. So for example, this makes it easy to split by task a dataset. Now, the data model is relatively simple. So if this is a benchmark instance, you typically are going to get at least a training stream and a test stream. Then you can take the training and split it to get the validation stream. And so the benchmark is basically a container for the streams. Then you can iterate over the streams to get the experience. Inside the experience, you have the information that is available at a specific time step. So like the data set, which will be a collection of samples. And then the data set, again, is an iterable object where you can get the single examples. So in the supervised continual learning setting, the most common, you are going to get the input, then the label, and finally, this is the task label if it's available. And streams are list objects, so you can take a specific experience or slice it like you do with lists in Python. Then the next component are the strategies. So there are lots of methods from the literature. I think at this point we have around 20 strategies, but there are lots of possible combinations that you can do with them. So it's like the number of combinations is very, very high, because these strategies are implemented as a thing that we call plugin. Basically, there is a training loop definition, and then most of the continual learning strategies are actually things that are adding some code inside the training loop, so you can combine them together as long as they don't interfere with each other. And most of the time, you are going to use a plugin from the library, but if you need it, you can also implement your own. And so this is an example, like here, this is the replace strategy, where the model is storing a small buffer of data to rehearse the past data. And again, you have the model, the optimizer, the criterion, and then the memory size, which is the argument specific for the replace strategy. And the training is just a loop over the experiences where you call the train method, and the evaluation when you want to evaluate on the test or validation stream. So as I was saying, training strategies can actually be combined together most of the time. So let's say that you want to make a replace strategy, which is also using a regularization like EWC. So you take a strategy, like base strategies like the naive fine-tuning, and you pass it a list of plugins, like here, replay and EWC. So this is like saying, do a naive fine-tuning plus a replace strategy plus a regularization strategy. And I mean, I think this is a very powerful feature of Avalanche, and I don't know of many other frameworks in PyTorch at least that allows you to do this with this kind of level of customization. And I mean, how to build a plugin is quite advanced feature, so it's I'm not going to explain it here, but the main idea is that you have these callbacks inside the training loop. So after the training loop receives the data set, you have the adapt train data set, so you can change the training data set. And then after the model has trained on an experience, you have this call after training exp, and so on. So by interacting with these callbacks, you can inject code inside the training loop, basically. So imagine that you want to implement a replace strategy. What you can do is that after the training data set is received, you expand the training set with the data from the external memory. So this just, you take the data set, you concatenate it with some external data, and you are done. And here, after each training experience, you want to update the buffer. So you take data from the current experience, you select the data that you want to keep for the buffer, and then you update the buffer. So overall, it's relatively easy to customize the training loop to your need. Then the third component are the models. As I was saying, models are PyTorch models, so you don't have to do anything custom here, but if you want, you can. We have some functionalities which are continual learning specific. One of these is the multitask support. So with multitask modules, you can have a model which is taking this additional argument in the forward pass, which is the task label. And the model is going to do different computations depending on the task label. This is something that is very common in continual learning. Like imagine a multi-head classifier is basically a model where you have a separate classifier for each task. It's something very easy and very useful when you have the task labels. And of course, the multi-head classifier is already implemented, so you don't have to implement it by yourself, but we also have the support for implementing custom module. Basically, you just need to implement the forward for the single task, and then the Avalanche is going to split by task and call the forward step for each of them. So on the right side here, you can see an example. This is a simple MLP, but with a multitask classifier, so multi-head. So the only difference is that here the attribute classifier is a multi-head classifier, and when you do the forward, the classifier is going to take as argument the input and also the task labels. The second features that you need to do continual learning is having dynamic models. So models that are growing over time, where you want to add units or entire layers maybe. And so simple example of this, the incremental classifier. So if you discover new classes over time, then at some point you will need to add some units to the classifier. The progressive neural network instead is an example where you take a layer and add some units over time. So this is something that PyTorch doesn't support in general, but we made sure that both the training loop and the PyTorch modules, in Avalanche, are able to deal with changing models architectures over time. So here it's an example of the incremental classifier, and it's inheriting from the dynamic module, which is the base class for the incremental models. And the only thing that needs to do is to define this adaptation method. The adaptation here is checking for whether or not the model needs to create new units. And if it needs, it's going to add the new parameters. And then you don't have to do anything. You just have to define the adaptation. But this is actually called internally by the strategy. So once you have a dynamic module, you don't need to care about this. It's completely transparent for you. And also the optimizer is updated to keep track of the new parameters. So everything will just work. Finally, the last part are metrics and evaluations and logging. So you have the evaluation module provides the metrics. Here, consider that metrics in continual learning are a bit more involved because you have the accuracy, but you have many different kinds of accuracy. You can compute the accuracy on the current experience, on the entire stream, or on the stream up to the current experience, for example. So each of these is a different kind of accuracy, and you have all of them in Avalanche, and it's very easy to select what you want. Overall, it's relatively straightforward, and you can also create your own metric. For example, we support Torch metrics, the metric library from the PyTorch Lightning. So it's very easy to take a metric from Torch metrics and put it inside Avalanche. Then the loggers are available also to report the results. And like here, you have an example of the TensorBoard plot. Here you see also the effect of the catastrophic forgetting, where you have the increase and then the drastic decrease because this is evaluated on the current experience. So, and all of this is integrated inside the training loop. So again, you define the kind of metrics that you want to keep a track of, the kind of loggers that you want, but then you don't have to call explicitly the loggers because it's done inside the training loop. And the training and eval methods also return a dictionary. So if you want to do something custom, it's relatively easy to do it by taking the dictionary and manipulate it. So now I just want to give you a brief overview of possible synergies between the continual learning and AutoML community. I mean, again, I'm not an expert on AutoML. I work on continual learning, but these are just the things that came to my mind. So maybe you find them useful, or maybe these are just naive thoughts. So the first thing, hyperparameters optimization. It's maybe kind of obvious, but actually in continual learning, it's most people tend to ignore the problem, or they do hyperparameter optimization, but they don't do it in a continual learning fashion. So the problem is that you have computational constraints, and this is already a big issue if you want to do hyperparameters optimization, which typically is very expensive. So sometimes people just take fixed values from the non-continual learning baselines. Like if you are going to train on ImageNet, you know what are the good hyperparameters of ImageNet from pre-trained models. So you just take those, and I mean, you are basically assuming that someone is going to give you the optimal parameters. Sometimes there is also the additional complexity that the best way is actually to change some values over time. For example, if you have a regularization strength coefficient, typically you want to increase the regularization over time, because if you have a regularization term which is telling you to not forget, the more data that you have learned, the more you don't want the model to forget. So you need to increase the strength of the coefficient. And then this is what most people do in research. So they just do model selection over the entire stream, which of course it's not continual model selection. So this is very bad, but what is most common in the academic literature at the very least. Some other people do model selection on the first part of the stream and then train on the rest. And again, this is problematic, but maybe it's the best that we have, maybe. Then the second large field in AutoML, neural architecture search. Again, this is for neural architecture search. I didn't see a lot of research related to continual learning. So in general, architecture in continual learning are either exactly the same as the non-continual learning baseline, but you also have this additional challenge that sometimes you want models to actually change over time, and you want also the architecture to change over time. So this is an interesting challenge to tackle. The only example that I know of continual learning plus neural architecture search is this work on deep priors. So they did neural architecture search, and if I remember correctly, they tried to find randomized models that were good for continual learning. So, and this is the deep prior part. And finally, for meta learning, like meta continual learning is a growing field. It's very hyped right now, I think, in the continual learning community, in the sense that, so if you work on meta learning and you want to start working on continual learning too, this is a really good moment for you. And in general, there are two different approaches. On one end, you have continual meta learning, and on the other, meta continual learning, basically depending on where you put the continual problem and the meta problem. So you can do meta learning on a stream, or you can do meta learning first and then do the continual learning. And like in my view, I think the best thing it would be to do to have a continual learning stream and then do the meta learning part inside, because otherwise it's just like a pre-training phase, but with meta learning. But of course, doing the pre-training phase is probably easier. And like these are some of the meta objectives that you see in the literature. So the idea is that you want to learn, but continually. So you can either optimize for fast adaptation to future knowledge. Like instead of focusing on catastrophic forgetting, so not forgetting on the past data, you can say, okay, I don't care about forgetting as much if I know that I can quickly adapt to the future knowledge. So when I see new data that I've seen before, but I completely forgot, I can still recover the performance very quickly. And then another kind of meta objective is the one where you minimize the interference between the old and the new knowledge. So you want a model that is able to learn, but by balancing, by explicitly optimizing this interference objective. Just to conclude the talk, I want to leave you some useful links so that you can start if you want to check the library. The first one is the link to the reproducibility repository. So here you have the script reproducing continual learning papers from the literature. In general, for each strategy in Avalanche, you can find at least one corresponding script in the reproducibility repository. We have also a more experimental continual reinforcement learning repository. This is called Avalanche RL. So, I mean, probably most of you are not doing reinforcement learning, but this is something that may interest you. Now, if you want to become familiar with Avalanche, you can check the official documentation website. And there you will find the two main tutorials, so the Learn Avalanche in 5 minutes and the From Zero to Hero. This one is basically a sequence of notebooks that is showing one module at a time. So at the end of this tutorial, you should have a clear overview of the library. And finally, of course, the API documentation. So if you're using Avalanche and you want some help, we are very happy to help you. Or you want to discuss new features, maybe possible improvement, like you feel that there is something important that is missing, just you can write on the Slack channel. This is the Continual AI Slack on the Avalanche channel, which is open, or you can open a discussion on GitHub. In general, we prefer discussions on GitHub because they are easy to track. So when we decide what are the next features that we want to add, if we have some topic on the discussions, it's easier for us to prioritize, while on Slack, things go missing very quickly. And of course, like if you find a bug, just open an issue. We are, I mean, as I was saying, this is really a collaborative project, so we are trying to engage as much as possible with the community. And okay, so this is everything that I wanted to say. So if you have any questions now, I'm happy to answer them.